So my name is Rousselene Larson, and I am a bioinformatics scientist at Utah State University. Today, I will be talking about in silico screening of natural compounds as novel drug targets for the treatment of multiple myeloma. So multiple myeloma is a plasma cancer. The white blood cell in the bone marrow. So when they are affected by multiple myeloma, they produce abnormal cells called multiple myeloma cells that we name M proteins. So the M proteins in the body, what it does, it can cause your immune system to lower, and it can also cause bone lesion as well as kidney damage. According to the American Cancer Society, in 2021, we had almost 35,000 cases of multiple myeloma, and half of those cases result in death. So we know that toxicity and resistance are correlated to the treatment of multiple myeloma. But we also know that plant-based natural compounds, they have bioactive components that are beneficial for the treatment of multiple myeloma. So we decided that we needed to come up with a technique that can show a comprehensive solution to the problem. So we decided to do molecular docking. So our objectives was to mine literature to extract those proteins that are responsible for multiple myeloma, and also extract the natural compounds that are available to generate the data set, and also perform docking and post-docking analysis to be sure that the complex that we find are suitable for what we need. And then from there, generate a list of potential candidates for the treatment of multiple myeloma, as well as having a web server out there that can serve the community, where scientists can go to access the data and use it as they see fit. So what is molecular docking? Molecular docking is the technique that allow us to study the interactions between two molecules. It could be protein-protein interactions, or it could be protein-ligand interactions, which is exactly what we are doing with our project. We are looking at protein-ligand interactions. And the type that we are using is the flexible type. So at the end of the day, we ended up having 16 serum protein that you can detect through serum protein electrophoresis for a cancer patient, 322 urine protein, and 41 LCP1 protein, and then 15 other types of proteins. And here's a method that we use here. Basically everything I've mentioned, but also wanted to mention that after the docking analysis, we were able to identify the top lead compounds and perform some post-docking analysis to check the stability and be sure that's the candidate that we need to use. So when we extract those proteins, we needed to have the 3D structures available. And to do that, we use the PDB database. And also for those proteins that did not have a PDB structure, we had to generate those structures by using homology modeling. And we also had to prepare the molecule before we do the docking analysis. That entails removing of water, stabilize the charges in there, and also filling the missing residue. Those proteins, when we extract them from the PDB database, they did not come ready. They have so many different active sites. So we had to decide which sites that we're interested in that are related to multiple myeloma and make sure that we are only concerned with those. As far as the natural compounds, we extracted them from ZEC and PubChem. But the most important things for us was to be able to follow the Lipinski rule of 5, stated when a compound bioactivity is suitable for oral absorption in human. So at the end of the day, we ended up with over 5,000 compounds from PubChem and over 100,000 compounds from the zinc database. So for the purpose of this presentation, I will only talk about 3 of those proteins. The first one will be IL-6, PDB-ID1ALU, which cause bone lesion in multiple myeloma patient, and TP53 that most scientists already know is the mother of all cancer in human, and the NRAS, which is one of the RAS mutation genes that can cause cell to go uncontrollably in cancer patients. So next, we are seeing here a complex structure of 1-ALU with its best dock compound right here, showing how it's docked to the protein, but as well as the amino acid responsible for the interaction that are occurring. And this is here for 2-BEEP, the TP53 protein, showing 2 H-bond interaction and a pi-pi stacking interaction. And the NRAS protein showing so many activity going on when the ligand is docking to the protein. So here's a table of more information on the proteins, their interactions, the type of bonds that they form, and the bond distance that they have. So the post-docking analysis, the molecular dynamics simulations, is to test the stability of the complex. We know that it's docked, we know that it's happening, but to know what's happening exactly, to know that the complex is stable, we have to perform molecular dynamics simulations. So what we did, we simulate our system for like 100 nanoseconds, all of them. And here, we also calculated the root mean square deviation and root mean square fluctuation of each complex. So here we are seeing the RMSD for the 3 proteins. Very perfect docking happen here. The deviation is well within the value, acceptable value. Usually it's 2 to 3 Armstrong. And we can see here at 40 nanoseconds, for example, for 1-ALU, we reach equilibrium and the complex stays there, which is an indication that indeed the natural compound is docked perfectly to the protein cavity of the ligand is docked perfectly to the protein cavity itself. So the RMSF calculation shows the same thing, perfect values. That's what we want to see, want the values to be 1 to 2 Armstrong right here. And this is a chart showing binding types of those interactions. For example, for 2-BEEP, we can see at 40% of the time, we had a hydrophobic interaction happening during the simulation time. So what we needed, so we had 342 proteins and we had over 1,000 natural compounds for each protein, not for all protein, but for each. And we needed to dock all these. The experts nowadays are taking 2 to 3 proteins, 5 max, because of the time consumption. So once we designed this experiment, we quickly realized that we did not have the time and we did not have the computing resources for this type of experiment. So a colleague of mine at the University of Utah refers me to the OSG pool. And I did not want to scale down the data because of the objectives that I had. So fortunately, once I started talking to Christina and her team, they did the best job possible to allow that I could run the data. The surprising thing about the data is the software that you use to do docking, it would have taken me 3 to 5 years to finish the project. And with the OSG pool, I was able to be done in just a month. So very grateful for the opportunity to not have to scale down the data. And here, the most important part of the project is to be able to have a web server implementation to allow the scientific community to access the data for themselves and to use it as they see fit. So here's an example of how a user can use the database. So let's say they put in a ligand and a receptor. So they will get in return the compound that's docked to the ligand and the receptor at the best binding affinity. And they are also allowed to see the top compounds, whether it's 50, 20, 100, 1,000, 100,000, we can offer that. They are also able to see the structure that's being formed and all conformation 1 to 10 and download that as well. So we know at the present time that there is no known cure for multiple myeloma. But with this experiment, our purpose is to show that plant-based natural compound is indeed suitable to help with the treatment of multiple myeloma. And we've seen that in this presentation through the RMSC and RMSF calculations. And we are excited to finish with the experiment. We are in our phase where now we are publishing the paper for both the database and the experiment itself. And again, HTCondor has made it possible, and it was a privilege to present that to you today.